Yeah. Right. Good morning. For those of you who don't know me, my name is Kevin Myers. I'm a network architect in the US with IP Architects. And today we're going to talk about using the MikroTik CHR as a BGP full table router. This is something that we've invested a lot of time in, not only in our labs, but with our clients to kind of see what that performance looks like and what you can do with the CHR as a full table edge router. So before I get into that, I'm going to tell you just a little bit about myself, my background. I started in the late 90s in IT and networking. We've spent about 20 years now in networking, 10 of it solely focused on network engineering. We've designed and built networks now on 6 continents. I think Antarctica is the only one we haven't put something on, and we're hoping the penguins will need Netflix at some point. MikroTik certified trainer, and I also hold certifications from MikroTik, Cisco, and Microsoft. One of the things I'm very passionate about is community involvement in contributing to a number of different network engineering communities. For those of you that listen to the Packet Pushers, I've been a podcast guest and blogger on there. You'll find me hanging out on Wisp Talk and Router OS groups on Facebook, if you guys belong to those. Network Field Day, I'm a delegate for Network Field Day, which is a group of people that go out to Silicon Valley and visit large major network vendors, and they kind of demo their next generation of technology. And we kind of talk about it in the state of networking and what's happening in network engineering, so check that out. You'll also find me on the MikroTik forum since 2012 under IPA Net Engineer, so I'm on there quite a bit. And also most recently Network Collective, which is a great podcast on network engineering in general. I talk about MikroTik quite a bit on that, and there's a lot of good content in there, so definitely check that out. And then just a little bit about IP Architects, my company. We are a global consulting firm for MikroTik. I think at this point we're one of the largest consulting firms in the world for MikroTik. We've got engineers in 5 countries, 3 continents, covering pretty much everything on the planet as far as consulting. We do managed networks, monitoring, load testing, development, and as far as our consulting, we do enterprise, data center, and ISP. So let's talk about what I hope you get out of this presentation. And this slide is in there for Giannis Megas if he's watching, because if you go through the MikroTik trainer course, he makes you put this in. The goal is hopefully that we're going to talk about the performance characteristics of the CHR on multiple hypervisors. So we purposefully used 3 different hypervisors for this testing to see what it would look like on doing the same tests on 3 different hypervisors. Some best practices when deploying the CHR, how do we build the VMs? What are the things we tuned when we were building the VMs? What did that look like? And then the benefits of using the CHR versus the CCR as a BGP edge router, because sometimes the CCR is a better choice and sometimes the CHR is a better choice, and it just depends on what kind of network you're trying to build. How many full tables are you putting on there? Are they truly full tables, or are they maybe a limited IX table plus a default? So there's a lot of mixes that make some difference in selecting that, in which way you go. So let's just take a quick overview and look at CHR versus CCR. Which platform is better? What are the throughput capabilities? x86 CPU versus Tolera, which is very important because a lot of the performance challenges that people talk about on CCRs and CHRs when it relates to full table BGP have a lot to do with the clock speed of the CPU and what the CPU is actually designed for to do. And then BGP updates, things like setting attributes, community local pref. Those are the things that can really bog down a table. It's one thing to learn a full table, but it's quite another to learn a full table at speed and then set local pref and send about 3 communities on top of it. And that's what can really bog you down if you need to do those to set policy in your border routers. So just kind of a quick comparison here. If you look at it, the x86 was generally designed for heavy computational work. It has a much higher power draw. You're going to spend a lot more time, energy, and heat getting the x86 to bear, but it's faster, on BGP full table. Tolera, on the other hand, was optimized for packet transfer at low power draw. That's why there's so many cores in the box, because the load gets spread out over multiple cores, which allows it to be a lower power draw. And so that's really what it was optimized for. So computationally, it's difficult to compare Tolera and x86 because they were designed and built to solve different problems. And then you look at throughput. x86 is actually going to take more than the CCR because it wasn't specifically designed for that. So you can make x86 move a lot of traffic, but you may have to throw more cores at it, more resources at it to move the data, especially when you get into lower frame sizes. Conversely, Tolera handles the throughput of different frame sizes, better than x86 because, again, it was a processor that was designed for the transfer of Ethernet packets. And then the routing table size, interesting thing here, I was actually talking to some network operating system developers out in Silicon Valley that write a well-known network operating system, and one of the things they told me is that the ASIC-based routers that you'll find in large network vendors are actually slightly slower to converge than a virtual machine because they actually have to spend time taking those routes and push them into hardware, and there's a delay time to actually get that into the ASIC for a large like chassis-based router. So a virtual machine actually can load a table faster than just about any router in the world because there isn't a delay between programming the RIB into the FIB that you have there. So the Tolera and the x86 actually have kind of a benefit in that aspect, is that it can get routes faster provided that you have enough speed to do it. And that's where x86 really kind of shines. So let's look at our test network for the CHR and kind of what we built this on. So what we did was we wanted to test this on a real-world platform, so we chose Baltic Networks. If any of you are familiar with Baltic Networks and their MaxWave products, we have one of their MaxWave Vengeance routers in our lab, so that's the router that we chose to put the CHR on, the box, which is it's an Intel Core i7. I think it's 4.6 is the clock speed on the cores. And we have that right here. So these are our two CHRs sitting on top of a single physical box that we were changing the hypervisor out on. And then we were running iPerf through it for load testing through these guys. But instead of using another virtual machine, we wanted to simulate an environment that was more like what you guys would see in your ISPs as you're peering with a real router. So we actually got about this big Cisco 7606 full table router, like what a large ISP would use, with 10 gig interfaces and high-end supervisors that can do more than 1 million routes in hardware. So because we wanted to have something that was going to be able to load a table into that CHR as fast as humanly possible, so we opted to have an actual piece of hardware instead of another virtual machine loading the tables. And then we've got a VM that we developed. Those of you that follow Stub Area 51, we've got a VM we built that'll load full routes. You can take them out of different databases. So we built some VMs that would take the full routes, and then they actually dumped them into a live router so that we could then stress test the CHR. So that's kind of what the setup looks like. It wasn't super complicated, just a couple border routers. We used a table from Lynx over here in Europe from the London Internet Exchange, and also from here in Germany we used DKIX because they're, at this point I think they're the largest IX in the world by volume of traffic out of the Frankfurt Exchange. So this is pretty basic. This is the setup, and then I'll kind of show you the hardware in the next slide. This is the actual hardware that we had in play. So that's a 6-slot carrier router. We had an HP server on the north end that was handling the VMs for both full tables. We had another HP server on the south side with 10 gig DAC cables. That was our throughput testing component. Then we had the Baltic Networks Vengeance hypervisor, which was what we actually loaded the different hypervisors and the CHRs onto, sitting on the south side of the 7600 here. And then we had another HP server sitting that we were doing iPerf. So that allowed us to load 2 full tables into the CHRs in various tests. And while we were loading the tables, we could light up a 10 gig traffic test into the CHR. So just to talk a little bit about what we did in the VM provisioning, what you'll find in licensing and hypervisors, and this is true of Esxi and their free version, and KVM, Proxmox as well, and Microsoft, is that 8 vCPUs is about what you're going to get unless you pay for some really high-end licensing. So KVM, for some reason, even though it's open source, won't let you assign more than 8 vCPUs. But we assigned as many resources as we could to the CHRs. The interesting thing that we found is that actually assigning the CPUs was not the major performance gain. It was assigning more sockets. So we actually assigned 4 sockets to the VM and then put 2 cores on each socket. And in the testing, that actually yielded a little bit better performance than just putting 8 CPUs out with a single socket. And again, I've mentioned this before, with BGP, single core performance is critical. So whatever CPU you select, it needs to have the most powerful single core performance that you can afford to put into the hypervisor, because you're going to spend a lot of time on that core doing that compute of that BGP table and the updates. So the higher the clock speed and the higher end processor, Xeon versus i7, the better off you're going to be. And then we went ahead and put 4 gig of RAM, which was way overkill for the 2 tables that we put in, but we didn't want to have any issue with RAM, so we put 4 gig into there. So here's the concept of testing that we went after. It was pretty straightforward. We wanted to do one BGP full table and just see pure speed test, how fast can it load a table. Then we wanted to load 2 tables with an iBGP peer between the 2 routers, which is probably very common the way some of you have it deployed in your networks. You have a couple of feeds for redundancy. You've got an iBGP peer between them. You exchange those full tables. And in a CCR, that can actually take quite a long time depending on where you're getting your feeds from and the state of the CCR. We've seen it sometimes take up into over 10 minutes on a CCR to do that convergence. So we wanted to test that. The next thing we wanted to look at was doing performance testing at 1500 bytes, 512 bytes, and 96 bytes. Because if you look at the makeup of internet traffic, the vast majority of the internet traffic falls somewhere in like the 500 to 700 byte range. So that actually takes more when you're using a CPU-based router. It's got to move. That's why Jumbo MTU gets you kind of a benefit if you're doing data center work, because that CPU can either move 9,000 bytes in one cycle, or it can move 64 bytes in one cycle. And so the higher MTU actually helps you move more data. But on the internet, you're varied between 64 and 1500. Now you'll notice something here. I used 96 bytes instead of 64 because we used iPerf to do our testing, and iPerf would not let you assign a 64 byte MSS in the TCP session. So 96 was the lowest we could get. And then the next thing we did was the throughput performance test with a convergence test. So we had a load on the router, we had a load on the CHRs that was somewhere around 5 gig, and then we knocked down all the peers to see how long would it take the peers to come back up under a 5 gig load to see more of a real world performance example. So a couple other things before we get into the tests. Sockets versus CPUs, more sockets is better. TSO, LSO, this is something that a lot of people don't get into, but is critical to have the best performance on a VM. So most of the servers that are built and the network cards have what's called TCP Check Sum Offload. So if you think about the way IP packets are built, you've got a checksum that's built into TCP that's going to look at to verify that what it has is what was sent and received. That's very computationally heavy, and so the VMware and Hyper-V and all these hypervisor manufacturers built this system called transport segment offload, load segment offload, and what it does basically is you'll also see it represented in things like RxTX offload or checksum, and it's designed to offload that really heavy computational process down to the NIC in the server. The NIC actually has some hardware that can handle that, and it sounds like a great idea. In real world practical use, it's horrible. It doesn't work very well. So most people disable it. And so, but a lot of hypervisors come with it on by default, so you have to go disable it. And if you look at the MikroTik forums, you'll see a lot of discussion about this, but you need to make sure that that's off on your hypervisor if you're having throughput issues on your CHR. And then clock speed. We said it before, but I will say it probably 3 or 4 more times. The highest single core performance that you can get is what you're after. So let's get into the testing and let's look at VMware. VMware is the first one that we did because VMware is what we've probably used more than anything else in the last year or two with the CHR. They're kind of the gold standard when it comes to virtualization. They do really well with a lot of things. And VMware overall is a great product. I love it, but we wanted to see what it would do for the CCR, or the CHR specifically. So what we did was we took the DKIX routing table, we pulled it from March, and we did a load time against just a single CHR to see what it would look like. And it loaded that in 26 seconds, which is actually, it's pretty good because that's, we're up to 680,000 routes now. So to learn 680,000 routes, and in some parts of the world it's 700,000, depending on who you are and where you are. But 26 seconds is not bad for a single peer. That's on par with just about any internet border router that you can buy from any vendor. So let's go forward and take a look and see what it looks like with 2 full tables. And here's where things get really interesting. So now I've got a full table here going out to a links table that we're feeding in. And then I've got a DKIX table. So we're at 1,000,002 routes somewhere in there. And now these 2 routers have got to talk to each other and they've got to exchange their table and say, okay, which one is the best path on this provider? Which one's the best path on this provider? And they've got to sort all that out. And that takes a little while. It took VMware, it took 4 minutes and 34 seconds. I'm sorry, 4 minutes and 46 seconds for that to fully converge using the CHRs on VMware, which is a little bit long. That normally you're going to see that on other platforms. You're going to see that converge a lot quicker than that. So let's look at our throughput test on VMware ESXi for 1500 bytes. So We did a 10 gig throughput test, but we had some other factors. So the goal of this was really not to see how much data we could put through the CHR, because we've done some other testing on that. It was to establish a baseline of testing and then repeat that test on every single hypervisor platform. So we did 5.3 gig at peak on this test through the CHR, and I think we had about 28% CVM CPU, so we still had some resources left to put more traffic through and fill up that 10 gig. And that's what it did at 28% CPU. So let's take a look as we drop our MTU. So now we've dropped our MTU to 512 bytes, and we go down to 3 gig with a CPU of 38%. So CPU is climbing because it's working harder to move what is the same amount of data as far as the CPU is concerned, even though the bit rate has gone down. And now we'll look at 96 byte MTU, and we can see that we've started to really dip down, and now we're at 1 gig. And so what this tells you, there's two takeaways from this here, is that because most internet traffic falls between like 500 to 700 or 800 bytes, that's like the average of internet traffic that's sent, you just need to put more resources behind your hypervisor. So whatever you select to put the CHR on, take into account that the numbers that you see posted by some people on testing the CHR may not necessarily be optimized for internet traffic. We've done multi-10 gig load tests on the CHR with data center specs where we do 9,000 MTU, and you can get it up that high. But when you're talking about internet traffic, you've got to take that down a good bit when you're scaling your resources. So now let's take a look at the 5 gig load test, plus we're going to converge both of these upstreams. So what we did was we disabled all 4 peers. We started the 5 gig load test, and then we lit all the peers up to see how long it would take for it to load the table and fully converge. And VMware took 11 minutes and 5 seconds to fully converge. So you can go brew a couple cups of coffee and do something else while that's converging. It was really, really slow. I was actually really surprised that it took that long on that hardware to do this full convergence test. So Proxmox. I'm sure a lot of you have dealt with Proxmox, have heard of Proxmox. What Proxmox is, for those of you that are not familiar with it, is a graphical front end to a Linux hypervisor, which is KVM. So Linux uses KVM, among some others, to do hypervisors. VMware got really famous because they had a really pretty graphical front end that made building VMs very easy, not on command line. So Proxmox is kind of an attempt to replicate what VMware has done, which is a graphical front end to the hypervisor to make it easy. So that's what we use, because I know a lot of people using it to do our testing on it. So the first thing you'll notice is that the speed of loading the full table is pretty close to VMware for the single table. 25 seconds. And one thing that we noticed that I would mention is when we would run this sometimes, I noticed that I would get varying results, and I finally kind of figured out that if you were to test it while the router was in the middle of its BGP update, which is happening every minute, that's when it would be a little bit slower. So you have to kind of take into account the state of the upstream router when you're doing this. But it was about on par with what we saw in VMware. So now we get into 2 full tables, and this is where things start to get really interesting, because if you remember, that time on VMware was 4 minutes and 45 seconds. So now we're into Proxmox KVM. We've run that exact same test using the exact same configuration on the CHRs and the exact same hardware underneath, but we are worlds better at 1 minute and 34 seconds for full convergence on this exact same routing tables. So obviously, with Proxmox there's definitely an advantage with Proxmox when it comes to the loading of routing tables. It is helping the CHR do it faster, and I think a lot of that has to do with in the hypervisor. Each of the hypervisors have a slightly different way in the way in which they move packets to and from the guest virtual machine. Hyper-V and Esxi and KVM all do it a little bit differently. So I think depending on what you're trying to do, Esxi may be great for standing up a Windows server or virtualizing a web server or something like that. But what we found is when you're trying to do network performance load testing, there were some little things that come into play that affect the performance. So let's look at the next one, the 1500 byte MTU test. And this was pretty close to VMware. It was a little bit lower than VMware. It was 4.4 gig using the exact same testing engines. And we had 28% CPU. So unless you're needing to get into like 20 and 30 gig performance on your upstream router, if you're doing like a gig or 10 gig, this one had 28% CPU. We had plenty of room to spare on that one. And then we look at the 512 byte MTU. Now this one starts to step down a little bit more than VMware. So this is where VMware had a little bit of an edge, was in raw throughput, because we're at 1.8 gig for the 512 byte MTU test, and then 29% CPU. So we step down into the 96 byte test, and we're down into 400 meg. Now VMware in comparison was like a gig. So all that really tells you is that if you want the advantage of the faster routing table convergence, you may have to put a little bit beefier CPU behind it, or spend some more time trying to tune the hypervisor layer and the network performance if you're trying to get really big speeds, because the VMware had a little bit of an edge in that department. Then the next thing we did was looking at Proxmox KVM, full table load plus bandwidth load. So if you remember, we did the same test in VMware. It was 11 minutes. Got a couple cups of coffee. Now we're down to, maybe we did 3 cups of coffee on the other one. Maybe we're down to 2 cups of coffee on this one, because this one did it in 9 minutes. So it was significantly and consistently faster. It wasn't awesome, but it wasn't great, but it was significantly faster than VMware. So now we get into Hyper-V, which was really the biggest surprise for me, because I haven't done a lot of virtualization with Hyper-V. Being mainly a network guy, I've mostly worked with Esxi for large companies. That's what they mostly use in their data centers, and a little bit with KVM. And so I hadn't done a lot with Hyper-V, but we wanted to load it to see what it would do. And right out of the gate, it was loading the routing table twice as fast as the other two. It was loading the routing table in 12 seconds versus the 25 seconds that the other two were doing. So that was double the speed of both of those. And then it gets even better, because if you remember, VMware's 4 minutes and 45 seconds for this test. Proxmox was 1 minute and 30 seconds for this test. Hyper-V did this test twice as fast as Proxmox, so it was able to load both upstream routers and synchronize its tables between the 2 border routers in under 1 minute. And that is on par with some of the best border routers in the world as far as performance. So that was a really impressive test to see that Hyper-V actually made the same config on the same hardware faster, just because it was a different platform underneath. And then we look at the throughput. Again, the throughput was roughly similar. Esxi kind of won in this category if you're looking at just raw throughput numbers, but it was close enough that it's not a major, I think, competitive difference between the two. And we did about 4.4 gig on this at 32% CPU. And then stepping down into the 512 byte MTU test, we got about 1,700 meg on this one at 33% CPU. So that was, again, not as good as VMware, but it certainly is not anything that would stand in your way of using it as a full table router. So that's not a major issue. And then about the same performance we saw in Proxmox as far as the 96 byte MTU. We're at about 479 meg and 37% CPU, using just all small packets. Another interesting point about this that I forgot to bring up on the others, often when you see a DDoS attack come in, they will leverage small packets because they're difficult for some devices to process. So those of you that have suffered a DDoS attack, you'll often find, if you go back and look at the packets, that a lot of them they'll send 64 byte packets in rapid sequence because it can kill a lot of devices. So understanding what your router can do at that low frame size is very, very important. And then we go back and look at the same test where this is the torture test, where we had the 5 gig load going through the box, and then we reset both of the peers, and I think they didn't put the right screen highlight in there, but it was 43 seconds for that test. So it was able to maintain the load and then maintain this exact same time that it took in the previous test of the 2 full tables and the IBGP peer, and it was able to do that in 43 seconds. So all the way around, as far as our testing, and we're going to continue to do more testing to kind of, we had somewhat of a margin of error in this because we didn't repeat each test like 200 times. We did do each test several times to have some confidence that the numbers we were seeing were fairly consistent. So I think what you're seeing are fairly accurate numbers, but if you want to get a true margin of error, you'd have to run it a few hundred times. But Hyper-V really kind of came out as a clear winner here. If you look back at it. And then one of the other things that I wanted to show you before I get into the ranking of the hypervisors is I wanted to show you a real world example of what this looks like in production. So one of my clients that's up in the Pacific Northwest of the US near Seattle actually agreed to let us share some of their data and a screenshot. So PogoZone is one of my clients. They're a WISP in the Pacific Northwest, and they use MikroTik everywhere. They have thousands of them. And we use the CHR as a full table router in one of their data centers. They actually have several that do full table routers. And we have a CHR and a Vengeance in one of the data centers here that I'm going to show you a screenshot of. So this is it actually in the real world, in production. So this was something we took from a few days ago. So there's 1.6 gig that's going through it. We've seen this one go as high as 5, 6, and 7 gig on a 10 gig link in the Seattle data center. And you can see the peaks that we're hitting here at 1.6 and 32% that's on the VM. So the hypervisor host underneath, which was the Vengeance, still had probably about 75% of its CPU load to spare. So we weren't, taxing the box, a whole lot. We had a lot more room to give it there. So that was an interesting test to go through, or to take that and compare it to the test. That, here's a real world example compared to what we saw in the lab. So which one is the best? I think it's pretty obvious. Hyper-V was head and shoulders above the Esxi and Proxmox in the lab. It was the most consistent with results. It was way faster in routing convergence on CHR than anything else. Proxmox is probably second because it had much better speeds than the Esxi, but not quite as good as Hyper-V. Esxi was really the only thing it did well in was just raw throughput, which is great, but if you already have enough compute that you cover the throughput that you need, I'd rather have faster routing convergence, and I think that's why we ranked Vmware Esxi last, even though throughput-wise it was a little bit over the other two. So, all right. So that's all I have on the presentation. That's kind of the testing that we did and what we found. I want to go ahead and open it up for any questions that you guys may have about what we did. Yeah, go ahead.
About the setup, did you take into consideration about your test setup? Did you take into consideration the Spectra and Meltdown patches?
I'm sorry, the what?
The Spectra and Meltdown patches?
No, I have not. The 641.3 is the version that we used. So, I really wanted to run it on different versions of the CHR, but because we did so many tests, I didn't have time to test all different versions of the CHR.
No,
so
I mean the underlay, Hyper-V and...
Oh, no. The Hyper-V, let's see, those were not patched, I think, for those. The ones that we used would not have been patched for those in those tests. So you would, to your point, you would probably expect a slight reduction once those patches have been applied.
Hi, Kevin.
Hey.
I would like to ask you just one question about, have you tried the same performance test for x86? If I'll just take the server itself, x86, and install the router OS there, and the convergence speed and everything, if you can share with us this results also, just to compare it with the CHR?
No, that's actually next on our list. There's two things I wanted to test that I didn't have time for. I wanted to test it as a container. So Proxmox actually has container networking so that you limit the loss in the hypervisor layer, and also on bare metal x86. So those were two that we didn't try in our testing, and maybe in a future MUM we'll rank those against that and go through that testing. That's a good question.
And also the question about the Quagga. So if you use the Quagga instead of MikroTik here, also some numbers, do you know the numbers?
So I can tell you, I've got some good friends over at Free Range Routing, which is the most recent version of Quagga, and I think they're seeing a load time of 1 million routes in like 15 seconds or something like that. Now that's done on a raw x86 box, so I don't know that there's a direct comparison over to the VM because they're doing it natively on Linux.
Any plans to test also Xen?
Yeah, Xen was on my list. I didn't have time to do more than 3 hypervisors, but Xen is also on my list of. So maybe we need a round 2 of this in the next MUM with Xen and containers and bare metal x86.
Yeah, and second one, in all the tests, did you have any other VMs besides the routers?
No, we had the only 2. The reason we used the Baltic Vengeance box is it was purpose-built to host the border routers. So the only 2 VMs that ever existed in there were BGP1 and BGP2, which were 2 different CHRs. All the other VMs that I used were on separate hypervisors on the HP servers that we had out. So these sat on their own dedicated box.
And how many physical cores did you have in these boxes?
That one I believe had a physical 4 cores. It was a Core i7. I can send the specs. If you go to Baltic Networks website and look at the Vengeance router, you can pull the specs on the CPU. They've got it on there.
Thank you.
Any more questions?
Nope. All right. Well, thank you very much. I appreciate it.